The next special diode then is the varactor diode. Varactor diodes are also known as variable capacitance diodes because the junction capacitance varies with the amount of reverse bias voltage. Varactor diodes are specifically designed to take advantage of this variable capacitance characteristic. The capacitance can be changed by changing the reverse voltage. These devices are commonly used in electronic tuning circuits used in communications systems. So if we think back on our capacitance fundamentals and characteristics about plates moving back and forth, surface area, distance between the plates, material and the dielectric, this all makes sense how we could turn this diode into something that acts like a capacitor. When the reverse bias voltage then increases, the depletion region widens, effectively increasing the dielectric thickness and thus decreasing the capacitance. When the reverse bias voltage decreases, the depletion region narrows, thus increasing the capacitance. Okay, so just think of what's going on between that PN junction, but think of it in terms of a capacitor now. So this action then is shown in the diagram. A typical curve of capacitance versus voltage then is shown in the graph below C. The typical varactor can tune over a 10-to-1 range of capacitances. Varactors are available in various capacitances or from approximately 1 picofarad to 200 picofarads. So we can see in the diagrams here what's going on here as we change the bias in terms of what happens with the regions. The dielectric widens and we end up with more or less voltage drop across the diode as we change the bias. And here is the graph of what's going on here with diode capacitance in picofarads versus the reverse voltage. So if we recall that capacitance is determined by the plate area, the dielectric constant, and the dielectric thickness D, we can go back to our expression. The capacitance is equal to the area by the dielectric constant by the dielectric thickness for our basic relationship for capacitance as it relates to the plate geometry and physics. In a varactor diode then, the capacitor parameters are controlled by the method of doping in the depletion region and the size and geometry of the diode's construction. Okay, so we can see here schematically what symbols that we would typically use and how we could come up with a typical equivalent circuit. Okay, some applications. Go ahead and read through the applications of varactors. The light emitting diode or LED, the basic operation of an LED is as follows. When the device is forward biased, electrons cross the PN junction from the N material and recombine with holes in the P-type material. Recall that these free electrons are in the conduction band and at a higher energy level than the holes in the valence band. When recombination takes place, the recombining electrons release energy in the form of heat and light. A large exposed surface area then on one layer of the semiconductor permits the photons to be emitted as visible light. And so this process is called electroluminescence. LEDs have come a long way in the past 30 years, from just being red and green. Now, you have entire spectrums of colors that can be produced, and the intensity is just incredible, even to the point that your headlights now are made for LED application. So we can see here then just a diagrammatic explanation of what's going on during the recombination. LED semiconductor materials, gallium arsenide was used in the early LEDs. The first visible red LEDs were produced using gallium arsenide phosphide. The efficiency was increased using gallium phosphide substrate, resulting in brighter red LEDs and also allowing orange, LEDs. The gallium arsenide LEDs emit infrared radiation, which is invisible, the symbol for the LED as shown. So the development led to being able to produce a green and a yellow, blue LEDs using silicon carbide, and ultra bright blue LEDs made of gallium nitride became available later. High intensity LEDs that produce green and blue are also made of indium gallium nitride. High intensity white LEDs are formed using ultra bright blue gallium nitride coated with fluorescent phosphors that absorb the blue light and re-emit the white light. LEDs emits light in response to a sufficient forward current. As shown in the figure, the amount of light output is directly proportional to the forward current as indicated by the graph. So there's your typical symbol for an LED, a diode with a couple little arrows on there saying that it's giving off light. And here is your typical packaging for an LED. The photodiode is a PN junction device that operates in reverse bias. Note the schematic symbol for the photodiode. The arrows are reversed. Photodiode has a small transparent window that allows light to strike the PN junction. Typical photodiodes then are shown in the illustration. Okay, you can see here the example here of on the schematic in A. You can see it's got a little lambda there. Lambda is typically used for light. Recall, when the reverse biased, a rectifier diode has a very small reverse leakage current. The same is true for the photodiode. The reverse bias current then is produced by thermally generating electron hole pairs in the depletion region, which are swept across the junction by the electric field created by the reverse voltage. In a rectifier diode, the reverse current increases with temperature due to an increase in the number of electron hole pairs. In a photodiode, the reverse current increases with the light intensity at the exposed PN junction. When there is no incident light, the reverse current, I lambda, is almost negligible and is called dark current. An increase in the amount of light intensity, then expressed as irradiance, and you can see the relationship there, M times W over centimeters squared, produces an increase in the reverse current. And so we can see the graph here of what's going on. Take a look at the application. Again, some fun stuff there. So those are your special purpose diodes then that your text has presented in this chapter 16 as it relates to semiconductors.